Thank you. Yeah, so I'm going to talk about Weil pairing, Boolean varieties, and introduce the general symplectic group, GS. Feel free to interrupt me with any questions. Yeah, so let's get started. So I'm going to first, okay, maybe let me give you the plan to talk. So first we will start with some basics about group schemes, and then we will introduce the Boolean varieties. Okay, over any field K, and then we will talk a little bit about isogenies, dual Abelian variety, duals and polarizations, and finally we'll define the Weil pairing and we'll look at its properties. And then we'll see what it implies for the GABA representation. So that's the plan. So let's get started. So I'm going to fix a base scheme. This is some scheme. I mean, it's yeah. Throughout this talk, it's okay to take S to be spec K. Right. Now, what is a group scheme over S? So it's a scheme over S with morphisms which give group structure. Yeah. So you have three different morphisms. This is the identity. You have the inverse. And you have multiplication. So these are morphisms of schemes, but they satisfy commutative diagrams which a group should satisfy. So, for example, one thing, the associativity law will be this commutative diagram. Where you first multiply, I mean, this morphism is, sorry, yeah, M cross, not the inverse, the identity. You multiply the first two things, and it's the identity on the last component, and this is identity M. This is M, this is M. So this diagram represents associativity. And then you have similar diagrams for all other group laws. Right? So that's a group scheme. Some examples of group schemes have GM. So these are examples of affine group schemes. GM is, we can write it as spec of this ring. So this is GM over Z, the multiplicative group scheme. So what are these morphisms? At the level of rings, the morphisms are going to go in the opposite direction. So E is, identity is the one that sends T to 1. So 1 is the particular identity. And the inverse sends at the level of rings sends T to T inverse, and M the level of rings. So this has to map into the tensor product of this with itself. So I can give two names. the names T1 and T2 for and the map is T goes to T1, T2. So it's the usual, it's the normal thing that you expect. Okay. Now you can also define GA completely similarly is spec and identity sends T to 0, inverse sends T to minus T, and M sends T to T1 plus T2. Okay. We will also be interested in like finite group schemes of the form mu n. So mu n is simply the n torsion subgroup scheme of G. Okay. So maybe I will say mu n. Yes, also okay. So these are all examples of affine group schemes. An abelian variety is a projective group scheme. So let me fix a field. Okay. Not going to assume anything about the field. So an abelian variety over K is reduced, connected projective group scheme. Okay. Some examples, like the most familiar example of an abelian variety is an elliptic curve. You can also just take a bunch of elliptic curves and take the product. So that gives some other examples. So these are dimension G varieties. But there are more abelian varieties of dimension D and dimension G than just products of elliptic curves. And one natural way to get abelian varieties is through curves. So I'll talk about this in a little bit in detail later, but let me mention this here. So let's say I have an algebraic curve over K, so G is G. And I can associate to it something called the Jacobian variety. So this is an abelian variety for K, dimension G. So these are some of the most concrete abelian varieties that you can work with. Okay. Are there any questions at this point? Okay, so let's move on. All right. So, I mean, these are, I just said these are group schemes, but I'm calling them abelian varieties. So it would be like super weird if the group law is not commutative, right? So thankfully that's not the case. So an abelian variety is commutative. So the abelian variety Let me give a proof sketch. It basically follows from from topology, from properness. Yeah, so since I'm working over a field, it's enough to just say that it's enough to work with k-bar points. And if I can just show that this map that sends x, y, x, y, x inverse, y inverse. What I'm trying to show is that this is always, this is a constant, this is going to identity. Right. I know that A cross E, let's call this as phi of A cross E and phi of E cross A are both just E. Okay. And so from here it's actually not too difficult. So this from here you can conclude that phi of A cross A is E. Yeah, so coming from this lemma that if you have a morphism of varieties A cross B to C, that A is proper, and if you know that phi of A cross some point B in B is equal to phi of some point A in A cross B, if phi is constant on both of these fibers, then phi is the constant map. Okay, so that's well and good. So we will just use plus to denote the group law from now. Alright, so the next thing that I want to talk about is isogenies. Alright. So firstly, what is an isogeny? Isogeny is a surjective morphism of group schemes. So it's a morphism of schemes which respects all the group structure with the size of the kernel being finite. Okay. So for any such isogeny, we have the notion of degree. So we will say that the degree of phi, just as in any other map, we can define it in terms of the function fields. So the function field of A is an extension of the function field of B. The function field of B sits inside function field of A under the pullback map. And so you can just look at the degree of this field extension that is the way to you just define the degree of the isogeny to be equal to that. Okay. Now, this extension need not always be separable when the field has characteristic 0. This is separable, but otherwise this need not always be separable. Okay. So if it is separable, then we can also say that this is exactly. So in any case, this is equal to the rank of kernel of phi as a group scheme. But we can say that this is the size of the set of geometric points if phi is separable. So this is always true if K has characteristics. Okay. Yeah, question?
How is the rank defined?
Oh, I think, yeah, so I think if you take a finite group scheme, we can break it up as the étal part and the multiplicative part and the local part. The étal part is exactly capturing all of the geometric points. But so if you just look at the dimension of that group scheme, you're only going to get this. But then if you also take the other two parts into account, then you get the entire rank. Okay. Yeah, that's a good question. Are there any other questions? Okay. So let me move ahead. So there is always, okay, yeah. So we always have the isogeny of multiplication by n. So this just sends any point x to x plus x. So we always have this isogeny. What is the degree of this isogeny? In characteristic 0, we can always appeal to, we can always go to complex numbers and then say that a set of complex points looks like a complex torus, AC, basically like G copies of the complex numbers quotiented by some lattice. So if you have this description, then you easily see what is the kernel of multiplication by n. Right? It's if you have this description, then you can just say that this is 1 over n lambda, and so as a group, it is going to be isomorphic to z mod n to the 2g, and so the degree of this is n to the 2g. Right? But I want to say this in general for any base field. So this is still n to the 2g. So let me give a proof sketch. So we are going to start by fixing a symmetric line bundle. It's a symmetric, very ample. Symmetric means that when I pull back by -1, I get the same line number. I can always ensure this by just starting with any line bundle and tensoring it with the pullback of it by -1. So I can start with just any m, just do m tensor -1. So let's say m is ample, let me just do m tensor -1 star m. Now this is symmetric, and then I can just raise it to a very high power. It will become linear. Okay. So this is one way to get such a line bundle. So we start from such a line bundle. I can think of L as being associated to this divisor B. Now, what is the degree of an isogeny? I can compute it by taking the full intersection product of this divisor. So let me take the G-fold intersection product. So there are G copies. I can also write this as so basically I'm going to claim that all of these are n square these. So I will get what I want if I can get this. I can finally cancel this off because it is complicated because of my assumption that it is very ample. Okay. So all I need to show is that pulling back by n changes my line bundle by raising it to the power n square. So that comes from the general formula for pullback by n. So for any line bundle L on A, the pullback by n is isomorphic to n square plus n over 2th power of L tensor minus 1 star L raised to power n squared minus n. Okay. So this is where I'm going to use my assumption that L is symmetric. So minus 1 star L is also L. And so I just add up the exponent and that is n squared. Okay. I'm not going to prove this proposition, but it basically follows from something called the theorem of the cube. So this is this is proven by induction. Using I am going to use this proposition later with skew symmetric line bundle. So for the skew symmetric line bundle, minus 1 star L will be L inverse, and so this entire expression will work out to just n. So n squared. So I'm going to use that later. All right. Okay. So now we will define the dual abelian variety. So if you have a pair, a check. So this is going to be the dual abelian variety, and this is going to be a line bundle on A cross A dual. It's called the Poincare line bundle. And then we will define this using some universal property. So where A dual is an abelian variety, okay. B is a line bundle. So this is the Poincare line bundle. So this will be called the dual abelian variety if two things happen. So you take this line bundle P on A cross A dual. For any point in A dual, if you pull back P to that fiber A cross B, you should get a line bundle of degree 0. You should get a line bundle on A of, you should basically get a line bundle in pic naught of A, which is translation invariant. So let me say that. Okay. Yeah. In pic naught of A. So this AB is the fiber A cross B. So if you take your line bundle and you restrict it to this fiber, you should get a line bundle that lies in pic naught, and it should be invariant in the translation. For all A in A. Okay. If you pick some point in, if you pick the 0 point here, and if you restrict your line bundle to 0 cross A dual, you should get the trivial line bundle. So those are the two properties that we want, and we want this pair to be universal with respect to these two properties. Okay. Meaning that if you have any other pair satisfying these two conditions, there must be a morphism from that abelian variety into a dual, such that the line bundle there is simply the pullback of this line bundle under the induced morphism. Okay, so that is the definition of a dual abelian variety. Now we're close to defining polarization. Yeah.
What's a map in condition 1? TA pullback.
What is the map where? Okay. All right. Okay. Yeah. So Mumford gave a construction of. Okay. Before I give the definition of polarization, I'll just say that polarization is basically going to be an isogeny from A to its dual. Okay. And Mumford gave a natural way to construct such isogenies. And also, I should say that you should think about A dual as parameterizing degree 0 line bundles on A. Degree 0 translation invariant line bundles on A. So every point in A dual exactly gives you such a line bundle. Yeah. So what is Mumford's construction? So we start. So we start with, if you start with a line bundle on A, let's say over A bar, and then you can define this isogeny by sending a point in A to this line bundle. I have to actually show that this line bundle is translation invariant because I said that A dual basically parameterizes translation invariant line bundles on A. So I have to show that this is translation invariant, but that basically follows from something called the theorem of the square. Let me not say more about this. Now I can define what a polarization is. So we basically showed that this, using that you can show that there is a homomorphism. So now what is a polarization? A K polarization on A is a K isogeny from A to A dual such that if you base change this isogeny to K bar, it should come from a line bundle on a K bar. So it should look like this lambda sub L. Over K bar, is of the form and this is not the same as saying that your line bundle is not the same as taking your line bundle over K and just doing this. That doesn't get everything. Okay. So that's a polarization. And then since it's an isogeny, you can talk about its degree. And if the degree is 1, you say that the polarization is called principal polarization. So it's principal if degree is 1. Now we can talk about the pairing. So let's fix an integer n. If you're familiar with the Weil pairing for elliptic curves, you know that that's a map that goes from En cross En to mu n. For us, it's not going to be a map like this. It's going to be a map from An cross A dual. The most natural way to define this Weil pairing is this way. You pair the n torsion points of A with the n torsion points of the dual to get nth root unity. Okay. So how is this defined? So this is canonically defined pairing. We'll talk about its properties later, but how is this defined? Let's take a n torsion point and let's take a line bundle. So it's n torsion, meaning that L tensor n is isomorphic to O. Okay. So remember that this L is in thick knot of A. So first I'm going to say that, this is where I'm going to say that for this line bundle, pull back by n actually gives you L tensor n. So if you remember, previously had pullback of an ample line bundle being L tensor n squared. This is a line bundle in thick knot, and -1 acts as pullback by -1 acts as -1 on thick knot, and so using that formula from earlier, this is simply L tensor n. Okay, so we have this isomorphism that the pullback by the isogeny n is the trivial bundle. So let's actually fix an isomorphism. So all this while I have just been working with this. Now I'm going to use the n torsion point that I have. So let's fix this. Let's take this isomorphism and let's pull this back by translation by A. Let's see if I do this there. This is and composed with translation by A. Back. Since A is an n torsion point, we translate by A and then subscribe by n. That's the same as n. So this is n. And translation by A of the trivial bundle is still going to be So what you have is now a different isomorphism from the same two line bundles, from the pullback of L by the isogeny n with the trivial line bundle. So you have two different isomorphisms. You can compose one with the inverse of the other, so you get an isomorphism of the line bundle O. Automorphism O, and the only such automorphisms of any line bundle on a complete variety has to be multiplication by scale. So this is just some scalar. You have to show that it is an nth root of unity, but that is not hard. You just show that Yeah, I mean, if you keep applying A to it, translation by NA is going to be nothing. It's going to be the identity map. And so zeta to the power n will be 1, and so zeta is in fact the root of unity. So we will define the pairing of A and L to be okay. Any questions about this construction? So if you look, I think in Silverman, Silverman's like arithmetic of ellipticals. Like he defines the Weil pairing here using like functions and divisors. This is essentially the same thing, just in terms of line bundles, and it becomes simpler. Okay. Okay. So what are the properties of this pairing, and why did I talk about polarization so much? Firstly, the pairing is between A and A dual. How do you get a pairing on A itself, the n-torsion of A? If you have a map from A to A dual, then you can pull back this pairing by that map. So that's where the polarization comes in. So we'll define it by using the same letters. You can define this if you have a polarization. This is a polarized abelian variety. ENPQ, ENP lambda. Okay, so properties of this pairing. Let's say first, yeah, En is a perfect pairing. So meaning that both the left kernel and the right kernel is 0. So if something pairs trivially with everything on the other side, then it has to be 0. So it's a perfect pairing. It's also Galois equivariant. Meaning that En PQ, sigma P, sigma Q is sigma of En PQ. Sigma is any element of the Galois. Actually, I'm listing all of these properties only for original pairing. P is an n-torsion point and Q is an n-torsion point. So this is an nth root of unity, and so here you have sigma acting on some nth root of unity. All right, and then so you have this pairing defined on n-torsion for all n, and these are compatible in the way that you expect. So if you take the mnth pairing and if you raise it to the power m, this is going to be the same as, so this is going to be a mnth root of unity. After raising it to the power m, it's an nth root of unity. It's going to be exactly equal to En mp mq. It's also compatible with isogenies. So if you have an isogeny between two abelian varieties A and B, you have a dual isogeny. If you think of points here as line bundles, this is the dual isogeny is obtained by pulling back line bundles. And if you give yourself a point in the n torsion of A and the n torsion of B dual, this is equal to n P of B. Okay. So it behaves well with isogenies. Now, if I look at the induced, maybe I should call it with respect to this polarization. If I look at this pairing, that is skew symmetric. So if I flip the coordinates, my root of unity gets inverted. And I am mainly interested in this pairing, and so I want to know when this is perfect. As long as the degree of this isogeny doesn't interfere with what is going on, this will still remain perfect. Okay. And this doesn't interfere if the degree is co-prime to n. Okay. If the degree is some prime which divides n, it basically means that there is some part of the, if the degree is L, some part of the L torsion of A which goes to 0 here, and so automatically if you take those points, the pairing will be 0. Okay, so it won't remain perfect. So E n lambda is perfect GCD of degree of lambda with n. Okay. Any questions on this? So I'm not going to prove any of these properties. I think, using the definitions, these are fairly straightforward. Okay. So I want to use this pairing to say a little bit about the Galois representations. But before that, so I said earlier that I will talk a little bit about Jacobians. So let's talk about them right now. So C is a curve, it's a nice curve, okay, smooth projective and all of the good properties, geometrically integral and all of that. Look at the Jacobian of C. So this is genus is G, this is G-dimensional abelian variety. If you just look at the points, the geometric points of the Jacobian, this is exactly fixed knot. Think of it as the group of degree 0 devices on C quotiented by principal devices. Okay. The one good thing about Jacobians is that these come with a canonical principal polarization. And that basically comes from Mumford's construction. So remember, so the polarization is going to come from some line bundle. I have to tell you what is L. I'll tell you the divisor associated with L. L is OD, with D is what is called the theta divisor. So what is this? This is the image of a certain map. So we can look at the G minus 1 symmetric power of C. And yeah, that has a map into a Jacobian. How do I define this? I'm going to define this completely by working over K bar. Over K bar, let's fix some point. So fix a point O on the curve. Then I can define this map and have G minus 1 points on C. I can send it to this divisor. This degree 0 divisor. So that is point on the Jacobian. So the image is going to be some G minus 1 dimensional subvariety. So that is my divisor. It's called the theta divisor. It doesn't depend on any of these choices up to equivalence. And so we have a canonical line bundle that's on A. So that gives rise to this polarization. Okay. So this is great because there is also principle, and so we have our Weil pairing on Jacobians is going to be perfect always for all n. Okay, so now finally we'll say a little bit about the Galois representations. Okay, so if you have an element of the Galois group, an absolute Galois group, okay, and if you have a point P in A, sigma of np is the same as n times sigma p. This is because multiplication by n is defined over, that is a morphism defined over k. So it's not changed by sigma. Right? So this means that if p is an n-torsion point, sigma of p is also an n-torsion point. So gk acts on the n-torsion of A. So this gives rise to a representation. We'll call it as rho n. And obviously this action respects the additive structure there. And so this is this lands inside this automorphism group. And now if I can say that this is equal to this is equal to GL to GZ mod n, assuming that n is different from the characteristic of the base field. Characteristic of K is co-prime to n. Otherwise, I have to deal with that separability issue. So if there is no such issue, then this is a 2G dimensional module over G mod n, and so you get 2G plus 2G matrices. That is the automorphism. Okay. Yeah. You can also so you have this for any n. You have these n-torsion representations for any n. You can take inverse limits in whatever way you prefer. For example, you can fix you can look at all the L power torsion representations and you can take the inverse limit, you get the L-adic Java representation. To fix L, you take all the L power Java representations, L power torsion Java representations, and you take the inverse limit, you get a map into the But there is also more structure on the torsion. There is the Weil pairing, and we also saw that the Weil pairing is Java equivariant. So, yeah, here. So we can actually say that this representation does not lands inside something smaller than just the group of all 2G plus 2G matrices. So I'm going to define ESP. So if you have any module over any ring, finite rank. So if you have a finite rank module over R, and if you have a alternating pairing, you can define the general symplectic group of V with respect to this pairing. So this is all linear automorphisms of V such that if you pair MV and MW, you should basically get the same thing as pairing V and W, except you're allowed to have some scalar. Okay. That could be some scalar, which does not depend on V or W. So I'm going to call this as Chisen M. So this should be true for all V and W. So this scalar basically defines a map from this group into R cross. So this is called the similitude character. Okay. So now what we are going to do is we are going to fix a symplectic basis of the N-torsion group scheme with respect to the pairing. So this is my alternating pairing on this group. What is the symplectic basis? So it's going to be, so this is a 2G dimensional thing, so I have I'm going to have 2G points here such that Pi and Qj pair to give a fixed nth root of unity if I is equal to j and 1 if I is not equal to j. And if you just pair any Pi with Pj or Qi with Qj, you're always going to get 1. So if you fix such a symplectic basis, so I guess I should also fix zeta at the beginning. So if I do this, then I can basically say that my N-torsion representation lands inside ESP2G Z mod M, which has an explicit description. So this this is the set of all M 2G cross 2G matrices. That M transpose Jm is equal to some scalar times J. So J is a matrix representing the pair. Because of my because the way I have chosen my basis, this is going to this pairing matrix is going to look like this. P1 and Q1 like pair non-trivially. That means my 1 comma G plus 1 entry should be a 1. Okay, so I can do this not just for any n. I can do this like consistently for all like prime powers. Okay. So if I fix zeta L power m greater than or equal, a consistent choice of L power m roots of unity is that if you take the L power m root of unity and you raise it to the power L, you get the previous one. So if you do that, then basically and you also fix your basis of the Tate module, the symplectic basis of the Tate module. Then your L-adic representation can be thought of as this map. And furthermore, like you know how Galois acts on roots of unity. That's what. Let me just say L power roots of unity. So this is called the L-adic cyclotomic character. I sub L. Essentially, this is defined as so. This is a character valued in ZL cross, such that this condition holds. And so your equivariance basically gives you that if you compose this representation with the similitude character here, what you get should be the L-adic cyclotomic character. The similitude character composed with the L-adic Galois representation is the L-adic cyclotomic character. Okay, I guess I'm over time. So maybe I will just say one thing and I will stop. So for example, if K is some FQ, a finite field, you can look at prop Q. Prop Q acts on roots of unity by raising it to the power Q. So the model cyclotomic character on prop Q is simply Q. As long as this is different from L. And so if you look at the image of Frobenius under the L-adic Galois representation, this lies in some coset. So it's some coset of the symplectic group, so the group that preserves the pairing exactly. So it's in the fixed inside GSP. with similitude Q. Yeah, so I will just stop.
Are there any questions for Shiva? If not, then let's thank Shiva again. We will reconvene at 9:20 tomorrow morning.